Hi folks, this is Dr. Mughal here. Welcome to my YouTube channel. Today we are going to do a very interesting project, and it is about the UART communication on Basis 3 board. I'm gonna go over transmission part of it today. At some point I'm gonna do the receiver part as well. This is probably the first time I am exposing you guys to UART communication. So if you don't have the background about the UART, I'll probably leave a link at the bottom of the screen so you can go and just do some reading and prepare yourself so you can better understand what's going on in this tutorial. What we are going to do here, we are actually going to build UART communication between the Basis 3 board that I have and the computer terminal. We are going to be using term, and I'm gonna tell you more detail about it in the later part of the video. What we are basically doing, we are actually using switches on the Basis 3 board, and we are going to transmit 8-bit data to the computer through the USB UART connector on Basis 3 board. When users uses those switches to turn on and off, they actually create an 8-bit code, and this will form a binary value of an ASCII character. Now this data, a byte, those bits, they actually will be transmitted through the UART, and the character will show in the terminal, in the computer terminal, and all the transmission is triggered when a button is pressed. There's also a button to reset the data as well. So it's fairly simple, but it's a very interesting project. You can actually add a receiving feature to it, and this could be a very good project for data electronics, or say any FPGA embedded systems or such classes. I also went ahead and created a top module. So in the red, what you see here is basically the top module. Okay, so this is our top module right here. Okay, so there are 3 different modules that we're going to work on. The one in the red is the top module. The one in the green is the button module, because you're using 2 buttons to reset and transmit. So we need to debounce that thing. We have already covered one lecture on this, on one tutorial. I'll also leave a link in the description for that as well. And one module would be the transmitter module. So in a top module, we will be instantiating this debouncing button and transmitter module, and subsequently putting everything together to make this project. So if I can just go through it real quick, we're gonna first work on the transmitter module, and the transmitter module is going to carry the 8-bit data 0 to 7. It's gonna have a clock. It's gonna have a reset button and the transmit button, okay, which will then go into debounce. So I'm not gonna worry about debounce, but this transmit out wire is basically reset and transmit. As you see this array sign right here. The output is going to be the TxD, because we are going to be serially outputting this data. So a bit we're gonna be using, and I'll show when we do the coding, we'll see we can get it to work through shift right register. Whenever the data comes in, it will actually start shifting 1 bit by 1 bit serially, and then at the output it's going to convert the data back into parallel. We are also going to add a start bit and stop bit. So for the UART, therefore it would be clear when to start shifting the data, or when the data is coming, and when all the data bits have been transmitted. So you're looking around a total bits of 10. which are going to be transmitted. One is going to be the stop bit, 8-bit is your data, 1 byte, and then you have the start bit. Okay, so you're looking at a 10-bit data which is going to be transmitted. So therefore it would mean we would also need a counter, we would need a shift right register that can accommodate these 10 bits. So let's get started. And also, you know, we will also be incorporating a state machine into this transmitter module, where basically the whole project could be sitting, could have two states. You know, one could be the idle state when it's not transmitting, and the other state is the when it is transmitting. There are 3 signals that we will be concerned, based upon which certain actions may take place. When shift is set to 1, that is when it starts shifting bit by bit. Load would, you know, start loading the data into the shift register, and clear would clear any past data that it may have. Okay, so let's start working towards the transmitter module. We know that we have 4 inputs: data, clock, reset, and transmitter, and we got 1 input. So let's get rolling here. So I'm going to put my inputs here. This is going to be the clock. We need the data, and we have 8 bits, so I just declare them as a bus. Sorry. Here, transmit, reset button, and then finally we have the transmit data. Again, we are serially outputting the data, so it goes 1 bit by 1 bit, 1 bit at a time. And that's pretty much it. I click OK here. I'm gonna start working on my code here. Okay, all right. I will also need few internal variables. So I'm gonna declare them as register. First thing that we need is a counter, and because we need to count like 10 bits have been transmitted, so we need a counter that can count up to 10. So 2 to the power 3 is 8, 2 to the power 4 is 16, so we would need 4 bits, and I'm gonna say this is my bit counter. Okay, I'll also do the commenting, so you can always go back and see what's going on every line of the code. This is going to counter to count the 10 bits. Remember, 8 bits is the data, and the 2 bits are the start and the stop bits. Now the second thing we need is basically a baud rate counter. One thing I forgot to mention in our block diagram, you know, we are looking at a baud rate of 9600 bits per second. Okay, and it is important for us to set that baud rate because we have a clock coming in, and also both receiver and transmitter, in case you have both, they have to be communicating at the same speed. Those of you who are not really familiar with the baud rate, it's basically the speed of the data being transmitted per second. There's also a formula to it to calculate the counter. So counter equals to clock over baud rate. Now we know the basis 3 board has a clock of 100 megahertz, and baud rate we need to set it to 9600 bps, so that comes down to I think 10,415. So 2 to the power 12 is 4096, 2 to the power 14 is 16,000 something, which covers this number, so that's why I chose 13. If you do 12, so 2 to the power 13 is like 8192 I believe, which is less than this number. Okay, so this is going to be a baud rate counter. It's kind of like setting a slow clock that we have done in our previous. Again, how I got this number, counter equals to clock, which is 100 megahertz, divided by baud rate, which is 9600. All right. Then I move on to the shift right register, and I have a 10-bit data, so I need 10 bits there. Shift right register. Okay, we have 10 bits that will be serially transmitted through UART to the board. Okay, all right. We also have two states. We just use declare them as registers, and those are, say, state and next state. Okay, and those are basically idle mode or transmitting mode. Okay, we would also need to declare our signals, which are shift, load, and clear as registers as well. Register shift. This is going to shift the signal to shift signal. Let me do it. Rephrase it. Shift signal. Start shifting the bits in the UART. Then you have this is a comment, so slashes over there. And then moving on to our second signal, which is the load. Load signal to start loading the data into the shift right register, and it will also add start and stop bits. Make sure you put those slashes in there. And then third signal, which is the clear register clear. This will basically reset the bit counter for UART transmission, and it will start the process all over again. Okay, now we're gonna break it down, and we're gonna first work on the UART transmission part of the transmitter module. Okay, so we are looking at the positive edge of the clock. Begin if reset. Followed by begin. State gets to 0, meaning basically state is idle. It's not transmitting at this point. When it's not transmitting at this point, the bit counter that we have should also reset itself to 0. Counter for bit transmission is reset to 0. And then baud rate counter should also set itself to 0. Followed by end, else begin. Okay, baud rate, this is when it's not in the idle state, it's transmitting. That is when you want the baud rate counter to increment by 1. Okay. And if baud rate counter reaches a value of 10415, which we got from here, okay, by putting the values in these equation, that is when the BPS is set to 9600. Then what should happen? Well, then we would want the state to move to the next state, which is the transmission state. I got underscored between next and state, so that's fine. All right, this is the this is when state changes from idle to transmitting. Okay. Baud rate is baud rate counter is supposed to reset itself to 0. Resetting counter. Once it reaches this number, this is when it reset itself to 0. Just like for a count, like a slow clock you do, it needs to get to a certain value and then reset itself and start counting back again. Now we are going to look at our signals, which were load. If load bit is high, what should it do? If load, meaning basically if load is exerted, well, it should actually load the data into the shift right register. So shift right register should get a value which would be, well, remember your stop bit is going to be 1 and your start bit is going to be 0. Okay, so comma, and then you want your data bits, which is the data right here. So you have your data here, and then followed by 1 piece. So the data is loaded into the register, and these are 10 bits because they contain start and stop bit as well. Okay, all right. If clear, what should happen? Clear is exerted. Well, this is when the bit counter should reset itself to 0. Okay, and if the shift signal is high, meaning if shift signal is exerted, then it should start shifting the bits in the shift register one by one. So shift right register gets shift right register, and then for shifting we use this greater than sign back to back by 1. So it will basically start shifting the data and transmitting bit by bit. Okay, and and because we have to make sure that 10 bits, when 10 bits are transmitted, that is when it should stop. So there has to be a counter, and when it starts shifting the bits in the shift register, the bit counter should also increment by 1. followed by end, because we had 3 begins, 1 2 3, so I should have 3 ends. Okay. This is done with the UART transmission part of the code. Now we are going to move on to the melee machine, the state machine. Again, going back here, we basically have 2 states. One is the idle, the other one is the transmitting. Okay, so we basically are going to apply case keyword to do our coding. Again, I'll start off with saying always add, we're looking at the positive edge clock, followed by begin. Load is initially going to be 0. Okay, so basically setting load equal to 0. Shift is also going to be 0 initially. Zero, so there's no shifting going on. Clear is also going to be 0. And TxD, which is our output, is going to be 1. When it is set to 1, there is no transmission in progress. Okay, right? So basically no transmission. Transmission will happen when the TxD is set to 0. Okay, now we can just apply case keyword to our state. Remember, we have 2 states. One is the state which is the basically the idle state. Okay, 0 begin. If transmit, meaning we are at the idle state and the transmit button is pressed here, then it is supposed to transmit the data serially to TxD. Okay, if transmit button is pressed, then the next state is equal gets a value to 1, which means it moves or switches to transmission state. Okay, load is supposed to set to 1 because it will start loading the data. It's okay. Shift is going to be 0 at this point because there is no shift at this point. Okay. And clear is set to 0 also to avoid any clearing of any counter. Followed by end, else, begin. This is, the condition if transmit button is not exerted or pressed, means it is supposed to stay in the idle state. So our next state is going to stays at the idle mode. Okay, and then the transmission gets to 1, set to 1, which we already know that this means no transmission. Followed by end, we have 2 begins, so we need 2 ends. Okay. The second case we have is basically when we are in a transmitting state. Transmitting state. Okay, this is when we are transmitting. Again, I'll go back here. We just did the coding for the idle state. Now we are in the transmitting state, so we are transmitting data. So we say if bit counter equals 10 by begin, then next state should get to 0. Okay. Basically it means it should switch from transmission mode to idle mode because all the 10 bits have been transmitted. Okay, this is what it means, and it should also clear the data. So the new data comes in, clear all the counters as well. Okay. Else begin next. If the bit counter, if it hasn't transmitted all those 10 bits, if that number is less than 10, say 4 or 5, only 5 bits have been transmitted, there are 5 more to come, then it should remain in the transmission state. So next state gets to 1. Okay, stay in the transmit state. Okay, TxD then gets to shift right register 0, which is the rightmost bit. Okay, and then shift should also be set to 1 because once the rightmost shift bit is transmitted, it should shift to the right, so you have a new bit that way. So this will make sure that you're continuing shifting the data. New bit arrives at the rightmost bit, followed by end. We have 2 begins, so make sure you have 2 ends right here, and then default setting you can set to next state is 0, idle. We're gonna finish our case keyword, so we say end case, and when we had the always at, so we use the end here again, and then followed by the end module, which should already be there out here. Okay, so I think our transmitter part is ready. I'm just gonna go ahead and save it and then run it. Looks like we have some errors. Let's see what those errors are. I might have extra in here, so that's why it's giving me that error. So I'm just going to remove it and save it. I still have that error. So line 87. In here that I need to remove here, and 98 begin I need to end this over here, followed by end and I think that should be it. So I'll just go ahead and save it. Looks like everything went through fine this time. I'm going to synthesize this. I was trying to synthesize it. It gave me a couple of errors. So let's see, line 63, shift right register is not declared. Well, didn't we declare that? We did. Okay, 63. Oh, it's misspelled. It's actually missing a G here. Shift right register. and line 75, a procedural assignment to a non-register. Ooh, so this output needs to be declared as register, okay, because it's transmitting. Okay, all right, let's go ahead and save it again. Click your source file and not implementation but synthesis. Okay, perfect, awesome, success. We're not going to worry about the implementation part at this point. Let's go back to our block diagram. Now we are going to work, this was the major part, like major success. Now we're going to work on the debouncing button. This is something we have done it already in the past. I'm just going to go through it real quick, and I'm just going to comment each line so you can always go back and understand what I did. So let's get started. And again, I'm just going to go back. We basically have the button that is going to be pressed, whether it's going to be reset or transmit. As an input, we also have a clock, and then we have the transmit out signal, which is going to be this right here. Okay, all right. Here I right click and I say add source file. I'm going to create a new file, and this is the transmit debounce signals, which could be transmit or reset. Okay, well, yeah, that's click OK, click finish. We are going to have clock as an input. We are going to have button, I'll say just button as an input, button for transmit and reset, and then we are going to have one transmit signal, which could be transmit. Okay, this is going to be the remember folks, this transmit is not the transmit, it's the signal, which could be transmit or reset. So that's pretty much it. Click OK here. Here the coding is not too long, but again, you know, like I mentioned, I'll just comment out everything so you can understand. So this is the basically the input clock right here of the board. This is the button, so input buttons for transmit and reset here, and here you have the transmit signal. Okay, we need some internal variables, so I'm going to declare them as registers. Button, we are basically using flip-flops here, D flip-flop, so button flip-flop 1 equals to 0, so this button flip-flop is for synchronization and initially set to 0. I'm going to copy and paste this over here. We're gonna need one more flip-flop, and I'm gonna use a variable name flip-flop 2 for this. Again, this is for synchronization in initializing the value, which is set to 0. We will need a counter here also, because we have 20 bits count for the increment and the decrement when button is pressed or released, and initially we are going to set it to 0. So 30 count initially set to 0, so 20 bits count for increment and decrement when button is pressed. It's gonna be really hard to optimize all these numbers because you know I have had difficult times when I would press the button, but sometimes it it doesn't give me the output that I would want. It would still give me like two letters, or what I'm trying to say is, like, when I input something, it basically generate two pulses instead of generating just one. So okay, so therefore I'm actually what I'm gonna do here, I'm going to add the parameter here, and you can tweak around with this value right here. I'm gonna go with 1 million. Okay, and see how your debouncing thing is working. Okay, all right. Here I'm gonna break it down for you guys so it's easier for you to understand. First, what we're doing is, first we are going to use the two flip-flops. I'm gonna use FF for flip-flops, so I can just write it down quick, to synchronize the button signal, which could be transmit or reset. Okay, and again, we are looking at the clock. And we say always at positive edge of the clock, followed by begin button F1 gets to button 1, which is basically this button right here. Okay, basically what's happening here, the input, the push button is actually feed it into the flip-flop. And again, I'll leave a link at the bottom of the video where you could go and separately learn about debouncing. So this is what it is. Whenever a button is pressed, the value gets stored in a flip-flop, and it's a D flip-flop. Button, there's another flip-flop 2, which is equals to button flip-flop 1, and these two flip-flops are connected in cascade. Okay. So therefore I'm using these two right here, these two lines. Okay, followed by and now one thing is, when the push button is pressed or released, we increment or decrement the counter. Okay, and the counter has to reach the threshold before we decide that the push button has changed. Okay, so again, this might be tricky, but again, feel free to gauge in and change this number around to make sure that you are getting a right, proper, stable signal. All right, now here we're gonna say always at positive edge of the clock. Okay, followed by begin if the button FF2 is high, meaning if button high, then if the count, I'm gonna just comment it here for you guys, if it is not at the count limit, then make sure you won't count up at the limit. Okay, first and all count, and then not the end. Count should go up by 1. Okay. And else begin if count. Basically what I'm saying here is if count has at least 1 in it, making sure no subtraction when count is 0. Okay, and again count goes up by 1, goes down by 1. Okay, this is when button pressed when the button is released on down, and I can write down here also, to write over there, when button is pressed, count goes up, count up. Okay, followed by end if count is greater than threshold, meaning if the count is larger than the number we mentioned above, then transmit is set to 1, mean debounced signal is 1, else transmit is set to 0, which means that debounced signal is 0. Okay, and module. So it's a pretty simple one. I did it a little differently than what I did in my previous lectures, but if you just go through the one of my tutorial, and again I would leave a link, that's pretty simple, and this is going to debounce the button right here. I'm gonna go ahead and save it. Looks like I got few errors. Let me just fix those real quick. Looks like I forgot to write clock here. So this one is done. Now I got 2 end modules, so I need to get rid of one of them. I'll go ahead and save it again. All right, went through. Going to synthesize it, which I normally do. Just make sure there are no errors. It may take a few seconds, so just be patient. So it went through perfectly fine. I'm gonna work on the top module now. Let's go back to our block diagram here. We have this debouncing button, we have the transmitter module. Let's put together everything. Again, our inputs would be data, clock, and then we have these reset and transmit. We have this transmitter as an output. Again, this is 1 bit because the data is being serially transmitted. We also have these other signals for the transmit, for the button that we have, for the clock, which is going to go through this UART, which is basically a micro USB cable, which is then connected to our laptop computer, and we are going to transmit the data through that UART. So we need to debug all those signals right here as well. Those would be considered as output. So let's get rolling with the top module. I'm going to add a new source file. and then I'm going to say this is my top module. Click finish, and here we have, so we have the data, and it's an 8-bit data, so let me declare it as a bus. We have the clock, right? We have the clock, we have the transmit, we have the button, which is the input signal for the reset. We have the output TxD, which is going to be transmitting 1 bit serially, and then we have debug, then we have this transmit, debug, okay, this we have this button, debug, then we have the clock, debug. All this will travel to that port through UART, and everything here is the output. Total of 1, 2, 3, 4, 5 outputs. Click OK. Okay, right. So this needs to be _. Okay, right. Everything looks smooth. Okay, now guys, remember what we are doing here. We are going to instantiate the transmitter and the debouncing module that we created. And in addition, we are going to create the following outputs and make assignment to debugging through the logic analyzer. But I want to start with basically instantiating the module that we created first. And because notice that we have a wire which is going into this transmitter module, so we need to declare this as a wire first. Okay, so I'm gonna say wire transmitting out. Okay, again, this wire is basically this going into this transmitter module. And I'll start with the transmitter, TRNSMI. Make sure your name of the source file exactly matches. T1. Now looking at the transmitter, what are the inputs? The input was a clock, data. So we have clock, reset, and then we have transmit, we have the data, and then we have the output transmission. And you can just go here, you get the clock, data, transmit and reset, clock, data, transmit and reset. The sequence doesn't matter, you can just play it around. Make sure you have like inputs separate by the output by a comma, and then you have this TxD. Okay, the second module that we need to instantiate is the debounce signal. So debounce signals, and here we're going to have the clock, the button, which is this right here, a clock button, and then the output transmit, and this is going to be this transmit out. So we're just gonna say transmit out. Now let's assign the functions here. the assign tx, I'm gonna start with this debug right here. Okay. This is I'm gonna use a lowercase d here. Okay. This is basically equals to that serial bit that is being transmitted, txd. Let me just copy and paste it so I can just change the parameters, input variable names. X transmit underscore debug is basically this transmit out. Okay. Remember the transmitter module has this input which is a transmit out signal, which could be reset or transmit. So that's why we are saying transmit underscore debug is basically transmit out, and then button debug is basically going to be reset right here, and then assign clock bug is going to be your clock. Everything is done. We got our 5 outputs right here, and then we assign our stuff that is going into the UART to the terminal. So let's go ahead and save it, and hopefully, yeah, you see the hierarchy right here. I'm going to work on my constraint file now. So I went ahead and imported everything that I needed to complete my constraint file just to save time. So here's my clock right here. Here's the 8-bit data. So these are going to be switches SW0 to SW7. The reason I got data in there is because that's how I have named it. Okay. To save time, you can replace it to SW, and by default the constraint file names them as SW. We need push buttons. One is for the transmit, the other one is for the reset. So this is the up button. This is actually the middle one, and the reset one is the up button right here on the board. Our outputs are, because we are going to be using the PMOD headers, it has to go through that UART. So we are using the PMOD header in the constraint file. You're going to be using those JA1, JA2, JA3, and JA4 because remember, I showed you on it's actually a 4-bit data that travels. Okay, so you would need JA1, JA2, JA3, JA4, which are these right here. Okay, and then the USB RS232 interface. We are only doing the transmission, so make sure you have this transmission output serially inputting the data. That's pretty much it. I'm gonna go ahead and save my constraint file, and it's about time that we should run implementation. There were a few errors. One of them is, so I misspelled it. Basically, I'm missing a M here. Gonna go ahead and save it again. Also, there were a few errors over here. Count is not declared, so I'm missing a T here. Troubleshooting is also, I could edit this video and make it short, but I just want to go through each and everything, and I want to also I want you to learn how to troubleshoot. Here, transmit is not. Okay. What I'm missing here. My transmit as register. Okay. Go ahead and save it. Hopefully everything goes fine now. Here's another error. It says threshold is not declared. Again, I misspelled threshold. One extra H in there. Go ahead and save it. Select your top module. one more error here. This should be transmit out. Yeah, let's go ahead and save it. Alright, looks like folks, the code is now ready. There were a couple of things that I actually fixed. One of them was the transmit was misspelled. Actually this one right here, which I fixed. This one over here, and also I did not let me comment it first. So this is instantiating the transmitter and debouncing signals module. Okay, so if you look at the transmitter right here, you have the data and the clock. So you have the data and the clock, plus I'm using transmit as a button, which could be reset or transmit in my top module. So I got transmit, and then what comes out of this debouncing module is transmit out. Transmit out, which goes into this transmit module. So this is how you would put things together. In a debounce signal, you got the clock, you got the button, and then you got the transmit out. Okay. All right, that's pretty much it. I just want to mention one more thing which I might have forgotten. I also had to change this to reset to BTN because that's how I named it over here. Okay, so make sure you make those changes. I'm going to save this file. I'm going to select my top module, click on implementation. It's going to take a few seconds before you can generate a bitstream file. All right, now it's about time to generate the bitstream file. The bitstream file has been generated. Now open the hardware manager. Already open. I'm just gonna make sure I have a connection, so I click open target, open new target, next. Just keep on, make sure your board appears over here, click next, finish. The last step would be to program the device. It should automatically select your bitstream file, click program, and you should be able to see the implementation of your design on the board. Well, really we don't have a design. What we're doing here is basically the communication between the board and the laptop, and what we have to do here is to set the logic using the switches and click on press the push button to transmit the data, and that would display the ASCII character in the window terminal. So after you have successfully downloaded your bit file onto the board, it's time that you should visit this website right here and download the tera term. Okay, it's a very small file and it should not take too long to download. I already downloaded earlier and created a shortcut on my desktop. So here, when you go here, you choose your serial port right here and make sure you have this connected. If you're using more than one serial ports, then you can always go to your device manager here and then look for what ports are in use. Okay, so mine is COM6 right here, which is this one right here. Make a connection, and now if I open the ASCII table over here with the code in hex, hexadecimal, decimal, and octal. So if you actually look at the ASCII code for A in uppercase, in hexadecimal is 41. Now if you look at the switches right now, they are actually making a code of 0 41. You got your A0100, actually 0100, and then that makes a code of 4, and then you got 000141, and when I should press the button, it should transmit the code onto the window terminal that should be seeable. I actually need to already have it installed. I just need to pull it right here. Make sure you put a check right here in the serial, click OK, and now I'm gonna press the button and you see that A. Now let's try. The reason you got those multiple A's is because the debouncing thing is not working as I was hoping. Let's try a different. Say you want to try N with hexacode of 4E. So you got 4 already set, and then you may need to pick AE, which is 1110 right here. Now if you send the data, let me switch to the terminal. Now if I send the data by pressing the button, you see N in capital, in uppercase. Okay, similarly, maybe we'll try one more combination. You see A here in lowercase, which makes a hexacode of 61. So here if this is 110, and then 1 would be, you got this 0, and the last one 1. So that makes a code of 61. And now if I press the button right here, it actually transmit A that you can see on the screen. So that's pretty much it from this presentation. I hope you have enjoyed this tutorial. It's actually a very easy one, but you can easily run into an error because of the number of lines involved in the code. If you have any question, feel free to leave it in the description, and if you haven't already, please subscribe to the channel, and I shall see you in the next video. Thank you for watching. Bye.